Hello, my name is Gwendal Simon. I'm happy to present here a paper that will be part of the ACM Multimedia Systems MMSys 2020 conference program. This work is entitled 3CPS, a novel supercompression for the delivery of 3D object structures. This paper is a joint work with Hristova, Vichy Swaminathan, and Stefano Petrangeli. Hristova contributed to this work while she was with IMT Atlantic, a French elite technological university. Part of this work has been done while I was in sabbatical at Adobe Research. The context of this work is a growing interest for the delivery of 3D objects in today's and tomorrow's applications. Gaming is obviously a key multimedia application using 3D content. We also see more and more demand for video studio, for 3D content, in particular to embed synthesized content into real scenes to generate photorealistic marketing movies. Of course, augmented reality, AR, is also expected to become popular in the next year, which would significantly increase the traffic related to 3D content in the network. A 3D object is basically composed of a 3D mesh, which is the geometry of this object based on polygons. The research community has produced a lot of work on mesh generation, mesh compression, mesh delivery. Another part of the object is a set of textures. The textures image are images which apply on the mesh surface to provide colors and material aspects. Then, the game engine processes a scene by applying lights, so typically with ray tracing techniques, and animation in order to generate photorealistic scenes, such as this photorealistic woman from Magic Leap. This paper deals with texture images, so let's have a deeper look into one typical textures which we downloaded from the CCO texture-free dataset. This rock textures, which applies here on the sphere, is based on 4 different images. The normal map indicates how the ray of light should reflect on the surface of the polygons. It makes the surface slightly less flat. The displacement map allows a game engine to actually change the surface relief, like changing elevation of the object of the polygons. The color map is the visual underlying color of the object, and the roughness map is, like its name says, an indicator of how the light should reflect. Other typically texture maps include metallic image and mask. For photorealistic 3D content, we need high resolution and high quality textures images. In this dataset, the images at the highest resolution and highest quality are 277 megabytes when compressed and 800 megabytes when uncompressed. You have to remember here that we are talking about only one textures, but complex 3D scenes may contain hundreds of textures. We obviously have a size problem here. When we look more closely at texture delivery, we identify 2 main bottlenecks. The first one is a network. The objects have now to be delivered from a server to a client as fast as possible, for example in augmented reality. The fastest the object arrives with all details, the best, because we cannot wait too much with low quality object like the right statue if we want to offer a good immersion in photorealistic virtual environment. The second bottleneck is for the processing at the GPU. The game engine renders a scene by accessing small pieces of the image in GPU. The main idea here is to extract and process texels. These are small blocks of typically 4x4 pixels. When a ray of light reaches a location in the object, the GPU extracts the texels and computes how the reflections applies. This means that the texels should be accessed independently from each other. This is what we call the random access features. Both bottlenecks matters when we study the state of the art. The traditional image compression algorithms, such as JPEG, HEIC, or WebP, can compress the original image by a factor of 25 or even more. So this is excellent for the network bottleneck, right? However, these image compression algorithms do not have the random access features. So to decompress the image, the client has to decompress and store the whole image in GPU. For the rock texture that we mentioned earlier, it would mean 800 megabytes in GPU for only one texture. This is not possible. The 3D community has addressed this problem by designing specific compression algorithms for textured images, such as typically the Savage 3D texture compression is a family of compression algorithms, also known as BC1, BC2, BC3. The idea here is to compress each texel independently. It is obviously very good for GPU random access. However, it's not as efficient as traditional image compression algorithms, so it is not good for the network. Another drawback of these algorithms is that they require a lot of computation to compress an image. The 3D community has thus developed another technique which is named Supercompression. Very cool name. The main idea here is that the server builds an image in a pivot compression format. This pivot image is decompressed at the client side in order to obtain a textured image. The supercompression is a good trade-off between high compression for the network and random access features for the GPU. It is still not as good as state-of-the-art image compression, but the result is overall satisfying. Our contribution is supercompression algorithm, which is presented on the right. Our solutions aims at using only well-known algorithms because they are already implemented in every 3D software and hardware platform. The main idea is that we perform 3 compression passes. 2 compression passes are done at the server side, which is not a big deal because these passes are done only once. On one final compression pass, which is done at the client side. This last step is critical and should require as less processing as possible. I will introduce now the details of our 3 CPS solution. The pipeline here should be read from left, which is the server side, to the right, which is the client side. At first we have an original high-quality image. Its size is generally 24 bits per pixels. We apply here a first pass with a texture compression algorithms. In this paper, we have focused on DXT1, which is the most basic and most used texture compression algorithms. Immediately after, we decompress the image. The main point here is that we obtain a texelized version of the image. What does it mean exactly? Let me detail one texel on the left. It contains 16 pixels with kind of similar colors as can be expected from a so small block of contiguous pixels. The main challenge of texture compression is to identify 2 endpoint colors. From these 2 endpoint colors, the algorithm derives a palette of 4 colors, and then it maps every pixel of the texel into this new palette. As you can see, the texture compression introduces some distortion in the image, like color changes. But this is the price to pay for random access and compression. The size of the compressed image is exactly 4 bits per pixels. So back to our pipeline. After the first compression, we have a texelized version of the image. Then we apply a second compression using state-of-the-art image compression algorithms. In this paper, we used WebP. These algorithms manage to compress the image so that the image size is less than 1 bit per pixel. It also introduces some distortions all over the image content. At the end, we have an image with a double distortion, but a very high compression rate, which is our goal for the network delivery. Then, at the client side, we receive a compressed image, but we cannot use it for GPU since it doesn't not feature the random access. So we have to compress it again with a textual image compression algorithms. Here is the main novelty of our solutions. Since the image has already been texelized, you remember the first pass, right? Then the image is almost texelized. I said almost because maybe the second compression pass introduced some noise, but hopefully not so much. It means that it is much easier to identify the 2 endpoint colors for an algorithm. Our main contribution is a specific algorithm that leverages the fact that the image is almost texelized in order to reconstruct a DXT1 image as fast as possible. This algorithm is integrated into the open source NVIDIA texture tool. The main advantage of C3PS is highlighted here. First, we have less than 1 bit per pixel for the delivery of the network. Second, we have a fast algorithm to obtain an image which has the random access features. Finally, we use only well-known algorithms. This is our main difference with the basis algorithms, which has been released a few months ago with Kronos GLTF group. Our solution can be implemented today, and it is immediately available for all 3D software on hardware platforms. So this is our paper. I may be a bit biased, but it is actually an amazing paper. This video is a really short introduction to the main idea of C3PS, but the paper contains many more details. First, we introduce the C3PS pipeline, which is what was shown in the previous slide. Second, we explain in detail our fast recompression algorithm, which is a key contribution for our solution. We called it the maximum difference cut. It leverages the fact that the image is almost texelized. Finally, we have a quite comprehensive performance evaluation against the basis algorithms. To the best of our knowledge, this is the first time the basis supercompression algorithm is evaluated in a scientific paper. In the paper, we answer some key questions, which I'm sure you ask yourselves. First, how texelized is the image that the client has to recompress? It is obviously super important in order for C3PS to perform well. We studied it carefully. Then we addressed two questions regarding the original objective of our work. How good is the compression rate for the network, and how good is the quality of the image at the end? Then one major question is the requirement of processing at the client side. How fast is the recompression at the client side? Today it is not reasonable to implement the basic DXT1 in a client device, but our algorithm in a new hope. Finally, we compare to basis, which is a very efficient and impressive competitor, even if it would require new implementation at the server and at the client sides. I don't want to spoil too much for those who are eager to read the paper immediately, but I would simply say that it is a tie. Sometimes basis is better, sometimes C3PS is better. Overall, both are comparable, but of course, the advantage of our solution is that it is easier to implement. The code source of the C3PS solution is available online in an open source in a GitHub repository. The URL is just here at the bottom. The committee of MMCs has granted us a reproducibility badge, which indicates that the code has been tested and validated. So feel free to join the community behind C3PS and to contribute for a world where 3D content is easier to transport at a lower processing cost. Thank you for your attention.